for me, it's a pleasure to introduce Sylvain Ervedoza. He is now Director de Recherche at CNRS at the Institut de Mathématiques de Bordeaux. And he is an expert on control theory and stabilization. And yes, he's a well-known mathematician. He has a lot of papers and citations. And he's going to talk about insensitizing control for the heat equation with respect to the boundary variations. So Sylvain, you can start.
Yes, so thank you, Diego, and thank you for this nice presentation, and thank you to the organizers for having organized this event. So even if it is only online, well, I think this is a great opportunity for us to share our work in these difficult times. So thank you very much for the organization. So today I'd like to speak about insensitizing controls for the heat equation with respect to boundary variations. So of course, if you do not know what it is yet, don't worry, I will explain it along the talk, and hopefully I will not lose you. Okay, so here's my plan, and my goal today is to discuss insensitization properties for a functional depending on the solution of the heat equation. So of course, in fact, I should define what is insensitization first. And in fact, the idea is to control a system such that there's a quantity of interest which is not sensitive to unknowns. So there have been a lot of studies regarding this question. And in fact, I think it started with a book by Lyons in '92. And of course, the answer will strongly depend on the system you consider, on the quantity you are interested in, and on the unknowns. What are the unknowns? Okay, so I will not review all the works on these questions. I will just focus on one, which is the one of interest to me today. So I'm sorry there will be a lot of notations. So I will spend some time of that talk just to on that slide, sorry, to make precise the notations. Okay, so here I have a time t. Okay, so I fix the time horizon capital T. Okay, and I will have three sets. A set capital omega in red. Okay, so this set capital omega is the set in which the equation takes place, right? So here you see the equation holds in 0t cross omega. Okay, so this set capital omega is the set in which the equation takes place. There will be two other subsets. So one set is small omega, which will appear here, and will be the set in which we control, right? So omega is small omega will be a subset of capital omega. And there is another set, theta, here, which is where we observe the solution, right? So here you see, well, I will focus on this functional, and in this functional there is this integral here over the set theta, meaning that I am interested in the solution only in theta. Okay, so there are of course much more things in here. So there is a source term psi, which is in L2 0t cross RD. Okay, omega is an open bounded, is a smooth bounded domain of RD. Okay, H is the control, right? So this is why it is in blue. It will act on small omega. Okay, it's here. I have this quantity of interest GH, okay, which depends on omega because capital omega is where the equation takes place, right? And so this quantity of interest here, you see, it's the total kinetic energy or the L2 norm of your solution in the set theta over time, right? So here, let me finish by perhaps the most important thing is to explain that this y here is the solution of the heat equation in my domain capital omega, right? With that source term psi, which is here and which will be fixed, okay, and with the control H. Okay, so here again, so I have y, which solves the heat equation with some source term psi, and my goal will be to design a control H such that GH of omega will not depend on too much on capital omega, right? This is my goal. So here again, this functional here, which will be my quantity of interest, is some observation, some L2 norm, right, of my solution on 0t cross theta. So theta is really the set in which I observe. H is a control, right, that I will choose, which will be localized in L2, L2. And I want to make this functional insensitized with respect to capital omega. Okay, so of course this problem is way too difficult to be handled in this full generality. So really, I will not be able to get a global result. What I will try to explain is how we can provide a local result, meaning that my goal is to design a control H, right, such that this functional GH of omega does not depend on small variations of capital omega. So of course, when you say that, you have to explain what it means, right? So I will take some time to explain what it means. But just before going further, I'd like to say that this is somehow a natural question, because in many situations, well, you know where you control, you know where you want to measure, or where you want your solution to have some specific behavior, but in fact you do not really know where is the external boundary. So here you see I am at home. If I want to control what happens here with a control which is here, probably I don't need to know precisely where are the walls of all the room, right? So this is basically the idea and the meaning of that question. Okay, so again here we will provide only a local result, meaning that we will discuss small variations of omega. So I need to express what I mean by small variations of omega. And in order to do that, I will follow the classical approach of shape optimization. Okay, so it is explained in many textbooks on shape optimization. So there's one I like by Antoine Auro and Michel Pierre in 2005, where it is well explained. So the idea is that you have a domain, so reference domain, okay, omega 0, which is smooth, but okay, you can forget about it. You have a vector field, okay, which is also smooth, quite smooth. So here is W3 infinity, okay, and then you consider the deformation of the domain by this vector field, right? So the map identity plus tau v is a diffeomorphism for tau small enough, right? So this omega tau v is the image of omega 0 by this diffeomorphism, right? So once you you have done that, you can consider the map which to tau associates GH of omega of tau v and try to see if it is differentiable or not. Okay, and it turns out that it is differentiable at time t at tau equal to 0, right? And when you compute the derivative at time tau equal to well, it's not a time, sorry, at tau equal to 0, you'll have this formula. So it will be the integral over 0 to t, the integral over theta of, okay, your reference solution, okay, which is, so this is the solution of the heat equation in omega 0, right, with the source term and the control, and some derivatives y dot v, right, where this y dot v solves this equation. So you see it's the heat equation set in omega 0 as the other one, right? But with non-homogeneous Dirichlet boundary condition, which involve v dot n. So in fact, this is a quite natural thing, right? If v acts only tangentially, when you look at the deformation at your set omega tau v in an infinitesimal manner, you are simply rotating your domain, right? So it's rather natural to see here this dependence in v dot n only. Okay, and when you have something like that, it's not so convenient to work with, right? Because at the end we would like to have something which depends on v. Okay, so if in order to do that, it's quite classical. You can introduce an adjoint equation and realize that this quantity, so the derivative of at tau equal to 0 of gh of omega tau v will write like this. So like the integral of on the boundary of v dot n times the integral over 0 to t dny0 dnz0, where z0 is the adjoint heat equation, right? So which is set in omega 0, and in which here you see you have a coupling with the first equation. Okay, and this coupling is appears in this observation set theta. Okay, so when you see something like that, you see already the equations are not so easy to deal with, right? So y0 will solve a forward heat equation, right, with a control, right? So the control is here. Z0 will solve a backward heat equation. So this is well posed. This is well posed. So no problem for well posedness. But the difficulty is that somehow you see here you want to control a quadratic expression in H, right? So it's y0 will depend in a linear manner with respect to H, and z0 will depend linearly on y0, right? So this is some kind of quadratic form, right? And to control y0, okay, you can do that here immediately, right? Somehow directly. But if you want to control z0, it will be an indirect control, right? Because you will control z0 through this guy, y0. So then I can make precise what is the question I'd like to discuss today, right? So here I have, again, so my functional is gh of omega. Okay, so it depends on h, the control, which I will choose depending on psi and omega. And there is this observation here, theta, okay, which in fact parameterize my functional gh. And the questions I'd like to ask are the following one. Can I have exact insensitization with respect to the boundary, well, at least locally, right? Meaning that, can I choose a control h, can I design a control h, such that for all v, the derivative of this functional at tau equal to 0 is 0. And well, of course, it's not a surprise that it will be very difficult to achieve. So we will also look at at a relaxed version, which I will call approximate insensitization, which is the following: for all epsilon positive, find a control H such that for all V, the derivative of GH of omega tau V at tau equal to 0 will be smaller than epsilon times the norm of V. So let me present the results now. So the result will strongly differ whether omega, so the control set intersected with theta, which is the observation set, is empty or not. And somehow it's very natural because, so here, remember, theta is your observation set, omega is your control set. So if they are distinct, it will be more difficult than if they are on the same spot, right? So this is the idea. So let me start with what should be the difficult case, right? So this is a result we recently obtained with Pierre Lissy in Paris Dauphine and Yannick Privat in Strasbourg. So when the control set and the observation set is of empty intersection, and when so this is somehow a technical assumption, when the observation set is strongly included in omega 0 and omega 0 minus theta is connected. So in fact, if you assume that theta is simply connected, you don't need that assumption, right? This is enough. Then what we can prove is approximate insensitization. We can also prove that we can also impose exact insensitization on a finite dimensional subspace, well, of the set of admissible vector field, which is W3 infinity. So let me perhaps mention that, well, it is well known, I think it has been done in the work by Fernandez-Cara and Zoazua, that when you have approximate controllability, then you will instantaneously have approximate controllability and exact controllability on a finite dimensional subspace. However, here it is not really the same phenomenon because the condition we have is somehow quadratic in the control, right? So this, I will try to explain that in the proof. So the proof, in fact, will be based on only an approximate controllability result and some kind of bilinear argument, which I believe is quite interesting in that context. Also, we have complementary results in the case in which the control set and the observation set intersect. Then we have, well, of course, we also have approximate insensitization. We can also impose exact insensitization on a finite dimensional subspace. But we can also do something which is quite interesting, is that we can also choose the control H such that it is an approximate control for the heat equation in the classical meaning that you can reach a neighborhood of any target data at time capital T, right? And in fact, we can even prove slightly more, but I will not have time to discuss that today, that if your source term can be null controlled, then you can further impose that your control H will be a null control for your solution Y0. Okay, so you see somehow the control you will design will be able to satisfy many conditions. So approximate control, approximate insensitization of the functional, and exact insensitization on the finite dimensional subspace. Okay, so here again, the proof will be based on an approximate controllability result and a bilinear argument. This approximate controllability result has to be slightly stronger than before, but it works more or less the same. Okay, and in fact, so this generalizes a previous work by Dessy, Privat, and Semporé, in which they prove that if omega intersected theta is not empty, then you get approximate insensitization and exact insensitization on a vector space of dimension 1 or 2. So here, this is arbitrary. Okay, so in fact, okay, this improvement is perhaps not the most interesting one, but what's interesting is that the proof is completely different and will somehow strongly use the quadratic nature of our condition. So let's go. So I will try to present some main ideas, let's say, of the proof. So the theorem 1 concerns the case in which your control set intersected the observation set is empty. Okay. So of course you will start by looking at what is this derivative here. And you see that we have this formula. So this is the one I presented you before, right? Where in fact this looks really much like a gradient of the functional, right? Because here we realize that this is v dot n against something. Okay, so in fact, if we manage to have this something which is to be smaller than epsilon, then we'll have the result, right? So what is this guy here, this something? So in this something we have y0, right, which solves the forward heat equation with a source term and a control acting on omega, and we have a backward heat equation with the coupling here with y0 on the observation set theta. Okay, and the strategy we develop is quite simple. We will choose h, so choose the control h, such that dn y0 and dn z0 are both smaller than square root of epsilon. So that this quantity here will be smaller than epsilon, and that will end the proof for approximate insensitization. Okay, so can we do that? Well, it looks like an approximate controllability result, but this is not the usual approximate controllability requirement, right? So here again, so we have, well, in a setting in which the control set and the observation set is empty, we'll assume that the observation set is strongly included in omega and that omega minus theta is connected. Then what we prove is that for all fy and fz on the boundary, so there are functions on the boundary, for all epsilon strictly positive, we can find a control function h such that the solution of this system of equations satisfies that the norm of the flux on dny and dnz, well, minus fy fz is smaller than epsilon. Okay, so here again, so what is this set of equations? So this is the control heat equation. So this is the forward control heat equation. It's controlled through omega. And the difficulty is that we also want to control z, in which somehow the control is indirect because it has to be done through y, okay? And this guy here is localized on the observation set, theta. Okay, so how do we prove that? Well, in fact, we will follow the very classical arguments saying that if you want the range of a linear operator to be dense, you have to look at the kernel of its adjoint. Okay, so and to prove that the kernel of the adjoint is reduced to 0. So let's have a look on the adjoint. The adjoint is this operator L star, which to g psi g phi associate psi localized on small omega. So again, this is a coupled system of heat equation, right? So psi will be the dual to y, and phi will be the dual to z. Okay, so here are the equations. So psi solves the the backward heat equation. So it starts from capital T, here is minus, right? With some non-homogeneous boundary conditions, which involve G psi, right? The source term here, and the coupling with phi. Okay, so what is phi? Phi is here, so it solves the forward heat equation with non-homogeneous boundary conditions. And the question is the following. If psi vanishes on 0t cross omega, can we conclude that g psi and g phi vanishes as well? Okay, so you see it's not completely clear, right? Because you only have that psi vanishes in the beginning. Okay, so let's have a look at what it means. So if psi vanishes in 0t cross omega, cross small omega, right? I recall you that here omega intersected theta is empty, right? So it means that psi in the connected component of omega minus theta bar solves the heat equation, right? And vanishes in omega, in small omega. So then you can use the classical unicontinuation property for the heat equation to say that psi has to vanish in this set omega minus theta bar. Okay, but then this set is a neighborhood of the boundary of omega. This is one of my assumptions. So then it means that necessarily psi is 0 on the boundary of omega, and so g psi equal to 0. It's very good. But then you see it seems quite delicate, because somehow we have almost no information here on phi, right? So we have to take some information on phi somewhere. And so this is what we do, right? We look at the equation here. Phi solves this equation, and what we do is somehow very naive. It's a kind of energy estimate, right? So we multiply this equation here by phi. And when you multiply by phi, so what you should have is a boundary condition in time, right? But in fact, there will be none here because psi at time t vanishes and phi at time 0 vanishes. There could be boundary conditions in space, but psi vanishes identically in a neighborhood of the boundary of omega. So in fact, there is non-boundary condition in space. So when you do the computation, so you multiply this by phi, boundary conditions are 0, right? So you can do all the integration by parts that you hope for, and you will get that the integral from 0 to t over the observation set theta of phi squared is equals to 0. So phi is 0 in this observation set theta. Okay, and then again, you can use the unicontinuation property for the heat equation, and it will tell you that phi vanishes everywhere and g phi equal to 0. Okay, so this is the proof of the approximate controllability result. Okay, but then it's not over. We'd like to impose exact insensitization on a finite dimensional subspace. So how do we do that? So I will try to convey the idea in the case in which this finite dimensional subspace is of dimension 1. So in this case, what we do? So first, we start by using our approximate insensitization result, so that we are almost already insensitizing in the direction of V1. Okay, and we are solving the approximate insensitization problem. Okay, so this is what we do. First we choose H0 such that the solution of this system of equation satisfy dny0 and dnz0 smaller than square root of epsilon. Okay, so then you already have approximate insensitization. Okay, so I will just replace psi by psi plus h naught, and I will forget about approximate insensitization. This is done. Okay, and then I will try to correct the small mistake we have on v1.n. Okay, so it means that I will look for control h such that this quantity exactly equals to 0. Okay, where y solves that forward heat equation controlled from h, right? And z solves that backward heat equation where you have here as a source term the coupling with y. So here I would like to strongly emphasize that this is a bilinear control problem, right? Because of course y depends linearly on the source term here, and z depends linearly on y, right? So this cross product here is a quadratic quantity. Okay, so how do we solve that? Well, first, I will do something which is, okay, quite painful to the eye, but I think the idea is quite simple. We want to distinguish what comes from the source term from what comes from the control, right? So everything so as I told you, y is linear in the source term, right? So I will decompose my source term as the one which is given, which is xi, and the one which is given by which I will choose, right? Which is the control part, right? So y xi and z xi are given, I cannot touch it, right? And yh and zh are quantity which are given here. So yh is the solution of the control heat equation of the forward control heat equation with control h, and zh is the solution of the backward heat equation with this coupling condition. Okay. So then let's have a look again at what I'd like to cancel. Okay, this quantity here. So in this quantity, you see somehow, so there are many terms, of course. If I write y as yh plus y xi and z as zh plus z xi, and so I simply expand this formula. Okay, and again, so here you have three terms. So the first term is quadratic because this is linear in h, this is linear in h. So this is a quadratic form. Second term here, this is linear in h, right? Because this one is given, this one is given, does not depend on h. And this one are linear in h. And the last one is a constant, right? It does not depend on h. So basically what we want to do is to find 0 of a quadratic form. So we know how to deal with that, right? But of course, it's tempting to say that, okay, we have a one-dimensional constraint, so it could be nice to look for control h in a one-dimensional vector space, meaning I will design the control h1, and I will look for h under the form h equal to lambda h1 with lambda and r, and h1 will be fixed. But of course, the problem is that then you'll have some quadratic polynomial like this, and this guy might never vanish. So then it seems that you are doomed if you do that. Well, of course, with some work, sometimes you can manage to do something. And this is what was done in the work by Lissi Privat and Simpore. But in fact, it doesn't seem to be very robust. And there is, well, I would like to advertise to a beautiful work by Bochard and Marbach in 2018, where they studied the controllability of non-linear ODEs with a scalar control when the linearized equation is not controllable, and when you look at what happens at the second order expansion. So if you do that, it turns out that the second order expansion is never a good idea to regain controllability, right? And this is also due to that fact, right? So when you have a scalar control, which is the case, somehow either you stay on a manifold, or you have some drift in some direction. So in general, this is a very bad idea to do that. Okay, so what we do is, well, in fact, very naturally, since we have a lot of possible choices to control and to choose the control H, we look for H in a two-dimensional vector space. So it's very simple, but it's very natural. And what will make everything work is that we can design controls H1 and H2 such that a quadratic form, when we apply it to lambda 1 H1 plus lambda 2 H2, will look like lambda 1 lambda 2. And if you do that, it's very nice because you can have a look at Q of lambda H1 plus modulus of lambda H2. It will behave like lambda times modulus of lambda. And then it is clear that this is a quadratic form which goes to minus infinity when lambda goes to minus infinity, and to plus infinity when lambda goes to plus infinity. So you will be able to solve easily this quadratic relation here. So in fact, this is also an idea that we have been developing in another context with Cherchendou Chowdhury in 2019, in a work on the controllability of Navier-Stokes equations with controls acting only on the normal components on the part of the boundary. And there we realized that the linearized equations were not controllable, and to control the missing directions, we were precisely designing controls in such a way that at second order, the quadratic form would look like that. So, well, can we do that? Can we really construct control H1 and H2 such that we have that this is close to lambda 1, lambda 2? Well, let's have a look at our quadratic form. Our quadratic form, of course, you can expand it again. So with the things depending on H1, the things depending on H2. And you'll see that what you want is that this quantity has to be close to 0. So this is the quadratic in H1, H1. So this is the term in front of lambda 1 square. Here, this is the term in front of lambda 1, lambda 2. And here, this is the term in front of lambda 2 square. So, okay, what we want is this guy to be close to 0, this guy to be close to 0, and this quantity here to be close to 1. So, in fact, we know some functions which will realize that, which are given here. So, gamma 1y equals to this, gamma 1z equal to this, gamma 2y equal to this, and gamma 2z equal to this. Okay, so this is a choice. There are many others, so let me just check that if you replace dny h1 by gamma 1y and dnz h1 by this guy, you'll have 0 here. Well, it's very simple. Here you see this is the integral over 0 to t. So of gamma 1y, gamma 1z, you look at the two terms, and in fact, at each time t, one of these two is always 0, right? So in fact, the integral from 0 to t of gamma 1y, gamma 1z equal to 0. It's the same story for the integral from gamma 2y times gamma 2z is 0, right? So this would be close to 0 if dny h2 and dnz h2 are close to these two. Okay, and you can check, well, it's not so painful, but I don't want to discuss that too much, please trust me, that if you replace dny h1 by gamma 1y, dnz h2 by gamma 2z, dny h2 by gamma 2y, and dnz h1 by this guy, you'll have that all this is close to 1. Okay, so of course we cannot take exactly dny h1 equal to this and dnz h1 equal to this, but we still have our approximate controllability result. So we can be close to this data on the boundary, and this is enough for our purpose. Okay, so we can get, for instance, that for all lambda in R, the quadratic form in lambda h1 plus modulus of lambda h2 is close to lambda times modulus of lambda bar up to an error of lambda square over 2. And then when you look at this map here, well, so again, this is a linear operator here, L. So this grows like modulus of lambda at most. This is constant. So by the intermediate value theorem, this will necessarily vanish somewhere. Okay, and besides, you will be able to have some estimate on the size of lambda in terms of this quantity, and this quantity, I remind you that they are small, so you will not destroy the approximate insensitization property. Okay, and in fact, you can really do that for any finite dimensional space. Okay, so maybe I will not discuss the proof of theorem 2 because I see that my time is running out. It's running, so I will just jump to some further comments. For exact insensitization, this is a much more delicate problem, and this is probably wrong in general. So what we know is that we have exact insensitization if theta is a subset of omega, meaning that your observation set is strictly included in your control set. But this is an almost obvious statement. And what we also know is that exact insensitization does not hold if omega 0 is smooth. And theta, so your observation set is omega 0, and your control set is a strict subset of omega 0. So the question is, can we exhibit a clear geometrical condition for exact insensitization? Personally, I have no idea. And of course, there are many related open problems. So first, in the case in which omega intersected theta is empty, can we further impose approximate or null controllability at time t? I have no idea on that. And the question will be different depending on the equation you consider. So for instance, it could make sense to consider the wave equation or Schrodinger equation. So for Schrodinger equation, it would correspond to some kind of probability density to find a particle, right? So that would make sense. But also it will strongly depend on the functionals that you are considering. So here I consider the L2 norm, but you could also consider the L1 norm if you think at some kind, if you think at the heat equation as an equation modeling the propagation of a density, right? Or the concentration of a chemical reactant. Okay, so I will stop here. Thank you very much for your attention.
Thank you very much, Sylvain. Is there any question or comment? Your argument, your strategy works in the case in which your equation has coefficients, or because I
would,
as soon as I understand,
I would say so.
Huh?
I would say yes, probably.
Because you use unit continuation, right? And
yes.
And as soon as the unit continuation is true, no, I think that
that should work indeed.
Yes, and also I think that it works in the case in which you have different kind of boundary conditions in the equation. I think also yes, no. For instance, Neumann boundary condition. I mean, the functional is going to change, right?
Yeah, the derivative of the functional will change. So
yes.
So for this, well, since I haven't done the computation, I will not say it precisely, but I would suspect that probably similar arguments could work.
Because your functional.
It depends on the look of the derivative of the functional, right?
Yes, yes. So in the case of Dirichlet boundary condition, you have the product of the normal derivative, right? So if in your equation you have Neumann.
Well, if you have Neumann boundary conditions at first, I don't really know what is the derivative of the functional. It might be much more involved.
Yeah, yeah.
So in shape optimization, in general, when you go to Neumann boundary conditions, the derivative is much more technically involved.
And my last question is your functional, you take it on an O, right? Which is a small part of your domain, and is it reasonable to think about a functional on the boundary? I mean, an integral of, I mean.
Well, it's reasonable, but then, well, you have to be clear to what it means to deform omega, right?
Mm.
So, well, for instance, if the functional is an observation on the part of the boundary which is fixed, and you deform omega only on some other part of the boundary, it would certainly make sense.
Mm-hmm.
Right?